There are different shapes associated with different names of orbitals. There is the s orbital. All s orbitals have a spherical shape. So a 1s orbital would look like that. A 2s orbital would be bigger. 3s orbital would be bigger than a 2. 4s would be bigger. There are also p orbitals. And for each energy level, there's no p orbitals with a quantum number equal to 1, but there are 2 p orbitals. The 2 means that n equals 2, and p is associated with the shape of a dumbbell. Now there are always 3 p orbitals within a given energy level. Energy level, we will say, is n, the quantum number. Sublevels are associated with these different orbital shapes. S, and now we're learning about p. So there are always 3 p orbitals within an energy level. So for 2p, there are 3 different flavors. There's 2px, 2py, and 2pz. All p orbitals have the shape of a dumbbell. Px is the dumbbell oriented on the x-axis. Py is an orbital associated on the y-axis, or oriented on the y-axis, and 2pz is the same shape oriented on the z-axis. So these all are meant to represent orbitals of the same size. That means that the electrons, remember electrons are found, have a probability of being found within these orbitals. All electrons found within 2px, 2py, and 2pz all have the same energy associated with them. And that is because, on average, the electrons will be located the same distance from the nucleus. Remember, the distance and separation between the positive nucleus and the negative charge of the electron is what gives it its energy. And the dumbbell, whether or not it's oriented along x, y, or z, has the same average distance associated from the center, which is, our center would be the center of this y-axis, and that would be the nucleus. There are also orbitals called d orbitals, and d orbitals have cloverleaf shapes. And there are 5 d orbitals within an energy level. There are no 2 d orbitals, but there are 3 d orbitals. There are 5 different d orbitals. 4 of them have this cloverleaf shape, and they are oriented and named according to how they're oriented in the axis. So dxz would have cloverleafs between the x and the z-axis. dxy would be in the xy plane. They're difficult to draw. There's better pictures. There's also dx squared minus y squared, and those are where the lobes of the orbitals are actually on the x and y axis. And there's also dxz. And then there's the 5th one, has what I call the pacifier shape. And it looks like sort of a pacifier with a ring around it. And that is called dz squared. So 4 of the 5 have this cloverleaf shape, and then the 5th one has this pacifier shape. They all even though I haven't drawn them exactly to scale, they all have the same average distance between the electron and the nucleus. And that's easier to see because for the other four, because they have the same shape, they're just rotated. Now, it's worth pointing out, say that all of these up here are 2p orbitals, px, py, pz. There are also 3p orbitals, and they would be called 3px. 3px would be the same shape and orientation as 2px, but it would be bigger. 3py would be the same orientation as, 3py would have the same shape and orientation as 2py, but it would be larger. And the same goes for 3pz. Again, because this shape is larger and the distance on average is further from the nucleus, the energies associated with these electrons would be higher in energy. They're less stable. Low energy means more stability, and higher energy means less stability and more likely to leave the atom.